Now, this experience with vectors you had with coordinates of vectors, it suggested to mathematicians that actually we can just take these columns of numbers and do these operations with them without any attachment to the geometrical meaning behind these columns of numbers. On one side, we'll lose something. What we'll lose? We'll lose the insight because we no longer have this geometrical intuition which might help us to get like a better view of the problem at hand. On the other hand, it opens to us possibility for generalizations. For instance, rather than considering columns of 3 numbers, we can consider columns of 4 numbers, or 5 numbers, or 1 million of numbers. Right? It might sound like a very unnecessary generalization, but it is actually something which is used very often. And that's what I'm going to just discuss with you on the next slide now, is this idea which comes from, it inspired by our experience with vectors, but it's no longer something we can visualize geometrically when we just take the columns of numbers and we start calling them vectors. So it's something which is called the space Rn. It's like a general title, which just generalizes this concept. So it will be a bit of a formal notations now for you, a little bit of it. So Rn, that's what it is. It's the collection of all the symbols like this. And these symbols, they're called n-tuples. N-tuples, that's the sort of a conceptual generalization from the couple, triple, quadruple. What will be for the n equal 5? Quintuple. Okay, quintuple. For the, if you don't know n beforehand, you say n-tuple. You may find it as an abuse to the English language, but that's how we do it. So this little symbol, it just tells me that we have a n-tuple of n elements. In expanded form, you will see it written like this. We're going to see it written like this. Yes, we're going to see you're going to see it written like this. So it's a column of numbers. This is the lengthy annotation. This is a short annotation. But in principle, that's what I will call. That's what your lecture notes, and that's what I will call n-tuples. The background behind this, again, let me repeat this: our experience with 3-dimensional vectors, where triples of numbers have a clear connection with the geometrical concept of a vector, and the connection I just explained on the previous slide. Now, with these n-tuples, or n-tuples, like I said, I'm not going to say n-tuples all the time. I'm going to say vectors or n-dimensional vectors. And every time I say that, you will associate with that some n-tuple rather than just a vector, rather than just an arrow. So with these n-tuples, just by doing this, like just extending our experience from triples, we're going to introduce the same operations like identification, addition, subtraction, and scaling. These 4, all we have to support our intention to study this is just they resemble a lot the vectors. Well, we also have they're useful for applications, but that's the other story. So here they are. So we identify 2 n-tuples. See, it's a 1 n-tuple in the short annotations, because if I write the column here like this, it will take too much space. So I write here the brief notation, but you can, in your head, you can expand it down to something like this. So if I have 1 n-tuple or 1 vector, n-dimensional one, if I have another n-dimensional vector like this, it's another n-tuple. This time it's filled with the b1, b2 dots b n take 1 b n. I identify this by saying that I will identify them component with component for every k, 1, 2, and so on. I will add them by building new n-tuple, where I will fill the entries with just per component addition. I will scale them again by building a new n-tuple, where I fill the entries with the per component scaling, or just multiplication. Length is trickier thing. Here, it's just like a form of definitions. I will call this quantity length, but strictly speaking, I don't have a right to call it a length, because why do you think it's a length? You've never been in the 4-dimensional space. You've never been in the 3-dimensional space. How do you know that the expression which I just model from my experience with 3 dimensions, like this, how do you know that this expression is the true length in this 4-dimension? You've never been there, right? So here you just have to, all you have to just rely on your experience with 3 dimensions, and just, you know, in 4 dimensions we trust, and we just, and we go with this. And the other thing which we can model again, you see I use the term model because I don't have any other evidence to support that. It's just I model from my experience with 3 dimensions. In n dimensions, I will be saying that n tuples are parallel. N tuples are parallel when I have a scalar such that one is a scalar multiple of the other. Again, I can't really support this anymore with the geometrical evidence, but we still persist with this language. Now, obviously, in terms of the notations, our well-known 3-dimensional space will have the notation like this. It will be R3. The plane, the 2-dimensional space, or the plane will be R2, and the line, which is 1-dimensional space, will be R1. It's just the variance of this new concept within the scope of our known 3-dimensional, 2-dimensional, or 1-dimensional space. What else I have to say this? Actually, I haven't finished this one. Did I? Sorry. This is just a nice abbreviation for the word exists. This one just reads exists. Thank you for asking this. So you read this exists lambda, which is a real number, such that this happens. Okay, this is just like a symbol which is used to abbreviate the word exist. Full stop, nothing else. Well, this is not finished, right? I mean, it's when the 2 vectors are parallel, it's not necessarily that this is true. Do you know what I'm talking about? It might happen that vector B. Well, it's okay. Well, officially speaking, I have to say like this: it's either one way or the other way. We have to test for both ways. So 2 vectors are parallel when one of them is a scalar multiple of the other. Which one? You can't decide beforehand. You have to just look into vectors before you conclude which one exactly is scalar multiple of the other. Of course, when your lambda is non-zero, you can always cancel it, take it on the other side. But when lambda is 0, you have to be careful. Even though when lambda is 0, it's sort of like a very marginal case, because when lambda is 0, one of the vectors will end up as 0 vector, which, you know, don't have either direction or magnitude. Okay. That's all I have to say for now for the Rn space. In the lecture notes or in your tutorial book, and here together with me, we will often now do some operations with n tuples of numbers. When the columns, these n tuples will have 4, sometimes even 5 elements. We will refer to them as vectors. We will sometimes use the geometrical language. Sometimes we say one is a parallel to the other. Or length, or sometimes we say the length of this vector. We might use some other geometrical terms in relation to these n tuples. All of these terms, they will be interpreted in some sense in terms of the components of those n tuples. How exactly they will be interpreted, it will come up in a due course. For instance, now these 2 pieces of the geometrical language in relation to the n tuples, that's how we interpret them. That's how we interpret the length. That's how we interpret the 2 vectors being parallel. Other concepts, as they come up, I will interpret them for you too. We will gradually start transferring the geometrical language and geometrical things we do with the 3-dimensional vectors to the n tuples of numbers or n-dimensional vectors.